All right, good morning, everyone. So, let's do one more example of displacement currents. Gavin already saw this yesterday because I didn't make it in your class, but I didn't do it in this class, but that's fine. So you can see it again. So this says that we have a parallel plate capacitor that has a circular plate of radius 30 millimeters and separated by a spatial distance of 5 millimeters. And then this thing has a sinusoidal potential between the plates, where that sinusoidal potential goes this way, which is 150 volts times sine of n 2 pi times the frequency, which frequency is 60 hertz, times the time. And this wants us to do two things. So A, it wants us to find what is the maximum value of the magnetic field directly at the perimeter of the parallel plates here, so right at the outside of them. And then finally, plot the magnetic field from any position inside of the plates, in this case. So I'm going from 0, actually, no, we're further than even on the outside. So we're going from 0 to then 10 centimeters. I guess I did it for inside the plates, but anyway, that's fine. We'll correct that today. So here's our picture. My picture looks like. So good. So again, here is my parallel plates, which are circular plates. So again, I have current coming in here, current going out here. This is AC source, so I have current going back and forth, which is then generating this potential. Here I'm just going to call this V0, which is 150 volts times sine of the 2 pi times frequency time, which then is going to create an electric field. And let's say at this moment, my electric field is pointing outward in this direction, meaning it's pointing this direction, and then it's only increasing in this case, just so we have a direction in which we can draw the magnetic field. Let's say this is my electric field generated by this guy. So good. So first, let's think about the direction of the magnetic field. So again, what's happening here is the time-changing electric field, which is generated by the time-changing potential, is then going to create a magnetic field, which we know has to go in circular lines. So in this case, our opposite of Lenz's law says that in this case, since the electric field is increasing, that means the flux is increasing. And since the flux is increasing, we have to induce an electric field in the same direction as the change, because we want to enhance the change, not kill the change. And so again, this is opposite of Faraday's law. So in this case, we want to enhance the change, which means in this case, our electric field, which is induced, must then point in the same exact direction as the exterior electric field. Since again, we want to enhance the change. So in this case, my induced electric field is going to be this way. Then modified right-hand rule number 3 says that if I'm going to put my thumb in the direction of the induced electric field, I can also curl around in the direction of the magnetic field, which means in this case, my magnetic field is going to curl around in this direction. So it's going to be my magnetic field, which means that we're going to choose our ampere loop to be exactly the same orientation as that of our magnetic field. So this is my DL, where this thing is just going to be at some radius of r. So the first thing we're going to do is actually then just determine the magnetic field anywhere on the interior, and then from there we'll specify at the radius of this object. So again, we know this radius has object has a radius of r. So let's just find what is the magnetic field anywhere on the interior, and then from there we'll specify for r is equal to capital R. So as we know from the Maxwell-Ampere's law, we have that the closed loop integral of the magnetic field dotted by the differential length is then equal to mu naught times the displacement current, because in this case, I have only displacement currents, not an actual physical current, since I'm looking in between the plates. Or this is then equal to mu naught times epsilon naught times the time rate of change of the electric flux. So let's deal with the left-hand side first. So in this case, again, we know that B and DL are in the same direction, which means the dot product simply becomes multiplication. So it's going to be then the closed loop integral of B times DL. And again, everywhere along DL, what has to be true about the magnitude of the magnetic field? It's constant, so it comes outside of the integral. So I guess it'd be B times the integral of DL. What's the integral of DL? L, and what's the length of that circle? 2 pi r. Good. So my left-hand side is then just B times 2 pi r. The right-hand side then is going to be equal to mu naught times epsilon naught times the time rate of change of the electric flux. Okay. Now, remember our electric flux, again, is equal to the integral of the electric field dotted by the differential area. But as we talked about yesterday, what's happening here is, remember, our area is always perpendicular to the surface, which means our area is going to be in the same direction as the electric field, or at least opposite to it. But we're going to choose to be in the same direction. So again, my dot product is simply going to give me multiplication. And what's true about the electric field anywhere inside of a parallel plane capacitor, at least as far as spatial orientation is concerned? Does it depend on position? No, it's simply a constant, which means this guy is going to become then equal to simply the electric field times the area. Okay, so then I'm going to take the derivative of the electric field times the area. Now, in this case, is the area of the plates changing? No. So here, this is then just going to become mu naught epsilon naught times the area times then the time rate of change of the electric field. Now, from here, let's specify, and let's say that we're looking at the interior. So let's now look at the interior. So when we're looking at the interior, that means R is less than capital R. So again, as long as I'm looking at the interior, what I care about then is the amount of area which is enclosed inside of this aperiod loop, because this is where my flux is actually passing through. So in this case, the area that we wrote down has to do with that area, which means for this case, my area then is simply going to be pi times local R squared. This is the interior portion. So let's look at this guy. So finally, what I'm going to get then is that what B times 2 pi R is then equal to mu naught epsilon naught times pi times R squared times then the time rate of change of the electric field. Now, for us, we're not given the electric field, but we're given the potential. So remember that the electric field is related to the potential by simply the distance between the plates, as long as the electric field is equal to a constant, which we already established that it is equal to a constant. This is true as long as this guy is constant. So again, we know it's constant, so I'm going to replace that. Now what we know here is that the spatial distance between the two plates, is that changing or is that constant? It's constant, so it's going to come outside of the derivative, and then we just have to take a derivative of the potential. So let's do that. So this is going to be then equal to mu naught epsilon naught pi R squared all divided by D times the time rate of change of the potential. So the potential has a V naught, which is also constant, so I can pull that out, and then it has a derivative of a sine. But what's the derivative of sine? Cosine times then the derivative of the inside. So good, let's put all this stuff together. So you know, mu naught epsilon naught pi R squared divided by D times the potential times the derivative of the inside, which is 2 pi times the frequency, times then cosine of 2 pi times the frequency times the time. Okay. So from here, we can now cancel out some terms. So I know this pi cancels out one of these two pi's. So let me cancel that pi. This R is going to cancel one of those R's. And then when I cancel, in this case, is that the interior magnetic field is then mu naught epsilon naught times R times V0 times 2 pi times the frequency times cosine of 2 pi times the frequency times the time, all divided by 2 times the distance. And what I want to do, cancel out those two. Okay, so again, this is the magnetic field anywhere on the interior. Now, again, let's go ahead and work on the exterior because we have to plot the exterior as well. So let's work on the exterior portion. So let's look at R greater than capital R. Now, the only thing that's going to be different is R greater than capital R is that now I'm going to draw my amperiod loop out here. So this is now my amperiod loop. So this is my DL, which means that what? Technically, the total area I care about is anything inside of the amperiod loop. But where's the electric field? Inside of this thing, right? Which means that the area I care about then is actually the area of the plates, which means the only thing that's different in this scenario is that my area then is then going to be an area of the plates themselves. This is going to be the only thing that is different. Otherwise, everything else is going to be exactly the same. So I get a B times 2 pi R is then equal to mu naught epsilon naught times my area, which is now pi R squared, divided by D times V0 times 2 pi times the frequency times cosine of then 2 pi times the frequency times the time. So the only difference now is that this thing is going as 1 over R, where the other one was linearly increasing as R. So again, let's cancel some terms. So now the only thing that's going to cancel is the pi's, and that's about it. So now I'm getting that the magnetic field on the exterior then going to be mu naught epsilon naught r squared times v0 times 2 pi times the frequency times cosine of 2 pi times the frequency times the time, all divided by 2dr. So this is my magnetic field anywhere on the exterior. What's up?
How do you determine the R on the left? 2 pi r, what R is that?
Oh, so that R is always just the R of the period loop that I draw. So that R is always just this R. So that is completely independent of where the electric field actually is.
Okay.
So it only depends on the size of the period loop that I draw. Right. So even though there's no electric field out here, that portion is independent. It doesn't care about where the electric field is. All it cares about is that there's a time-dependent electric field, which is creating a magnetic field. Okay. Is that okay?
Yep. Okay. So in this case, the induced electric force is in the same as is the same as the electric force in the
right. So the induced electric field is still in the same direction as the electric field, as long as this guy's increasing. Now, when this thing starts to decrease, since it's sinusoidal, what happened then is that the induced field will be in the opposite direction, or be inward instead, which means the B field will go in the opposite direction, which means in that case we'll take DL in the opposite direction. So here I'm just drawing it so we know what it actually looks like. But mind you, what's actually really happening here, since the potential is constantly oscillating back and forth, this is creating magnetic fields that at one point will go this way, and then we'll go this way, and then we'll go this way, and then we'll go this way. So it'll be constantly changing back and forth. So, but again, since I'm only looking for the magnitude, I'm not worried too much about that. It was okay? Sweet. So, good. Now we have two different solutions. So we have this guy for the interior, and we have this guy here for the exterior. And now what we want to do is what? First, find out what is the maximum that either one of these things are going to be. So basically, if I look at this, what I want to know is what is the maximum value that this thing could be as a function of time? Meaning, what has to be true about that cosine term if I want this thing to be its maximum value? It has to be true about cosine. So this thing is going to reach its maximum value as a function of time. What's the maximum value cosine can be? 1. So basically, to have a B max then, which is what this question is asking for, what has to be true then is that this cosine term simply has to be equal to 1. Right? So that's on the interior. Well, what about the exterior? Well, it's the same thing. For this thing to actually be a maximum as well, what has to be true then is that the cosine term has to simply be equal to 1. Otherwise, it's going to go somewhere between -1 and 0 back to 1. So for this thing to be its maximum, what I care about is that the cosine term is simply equal to 1. So let's write that down. So in this case, for B max, we require cosine term, let's write this as omega t, equals to 1. This is what's going to give us B max. Good. So in this case, we then have for the interior, we then have that B max as a function of R is then going to be equal to mu naught epsilon naught R B0 2 pi times the frequency all divided by 2 times B. And then for the exterior, we then get that B max as a function of R is then equal to mu naught epsilon naught R squared B0 2 pi times the frequency all divided by 2dr. Now we can finally answer part A. So part A then says, what is the B max at R is equal to big R? So little r is equal to big R. Now, for that case, it doesn't matter which one of this we use. We can use this one or we can use this one. We get the same answer at the end of the day. So if I use this one, all I'm going to do is evaluate this at what, big R, which means this is simply going to become a big R. If I evaluate this one at big R, this one is going to become a big R, which is going to cancel one of these big R's, which gives me exactly the same solution. So it doesn't matter which one I use. So let's just write down one. So in this case, what I finally get then is part A, B max at R is equal to capital R, is then going to be mu naught epsilon naught capital R B0 2 pi times the frequency divided by twice the distance. Plug in my numbers, but again, in this case, then it works out to be 1.9 times 10 to the minus 12 teslas. So this is the maximum value of my magnetic field. Okay. Part B then says plot. So let's go ahead and plot this. So in this case, we want to plot B max as a function of R. Now again, to plot B max, the same thing that we've done plotting before. All we're going to do is go back to our two expressions and then look at what is the R dependence. So what's the R dependence in this one? How does it depend on R? Little r. Little r that shows in arrow points. What kind of dependence is that? Linear, right? So on the interior, this thing is simply growing as a function of R. It means on the interior, it's doing this. That's it. In this case, I'm going to get to this point, which is then R is equal to capital R, at which point I'm going to be equal to B max capital R. So this is where I reach my 1.9 times 10 to the minus 12 teslas. Cool. And then on the exterior, what's it doing? What's its R dependence on the exterior? 1 over R. Good. So this is then just simply that. This thing is eventually going to go to 0 as R goes to infinity. 1 over R dependence here, and an R dependence here, latest. And that's it. So good. So our next topic is to talk about how do we actually generate light. So how do we generate light? Now, I'm not going to go through the mathematical derivation of this, mostly for two reasons. Number one, we never actually talked about the wave equation when we did waves earlier. So if I derive the wave equation now, you just look at it and be like, that looks great, but I don't know what that means. So it's kind of pointless. And in that case, again, it's kind of pointless. And the other reason is it uses a lot of concepts from Calc 3. And I don't think anybody in here, maybe one or two of you weren't actually in Calc 3, but we're going to skip that. So instead, we're going to kind of motivate it by looking at an example. And let's think about our example. So our example is going to be what we call radio waves. In this case, we're going to look at what's known as a dipole antenna. And let's use that to kind of motivate what's actually happening. Now, as we talked about yesterday, what happens then is when it comes to generation of light, basically Gauss's law has nothing to do with it. Right? What's actually happening is that it's an interplay between Faraday's law with the fact that I have to generate a time-dependent electric field, which generates a time-dependent magnetic field, which goes back and generates a time-dependent electric field. So it's a circular kind of pattern between the two. Which means that because Gauss's law has nothing to do with it, Gauss's law only deals with stationary charges or constant currents, which means that to generate light, I can't have anything which is static. I have to have a time-dependent magnetic field or a time-dependent electric field, which means I have to have some sort of changing currents, which means I have to have an acceleration. So we generate light by the acceleration of charged particles. So what actually generates these then is the acceleration of charged particles. So any charged particle which is actually being accelerated is going to radiate away light. Again, this is the aurora borealis, things like that. We see when this thing is undergoing uniform circular motion around it. What you're seeing then is that generation of light due to the acceleration. So let's have an antenna. How does an antenna actually work? So the way an antenna works is I basically have two rods. Here's rod number 1 and here's rod number 2. And these guys are going to be connected to something which is generating a alternating current. So I'm going to have an AC source here. So what happens? So let's say initially at t is equal to 0, the charge is equal to 0 and the current is equal to 0. Okay? Just for context. Now what's going to happen then is as time goes on, charges are then going to move from my AC circuit in this direction. So I'm going to start building up positive charges on this side and then start building up negative charges on this side. So what's going to happen then is what over time, I'm going to start creating that this thing becomes positively charged. Meanwhile, this guy is going to become negatively charged. So in this case, what happens then? Well, if I have positive charges on the top side and negative charges on the bottom side, what must I create? Magnet, we're going to get there in a second.
Magnetic force.
Good, but what comes before? So moving charges creates a magnet. But if I just have charge separation, what do I create? An electric field. So what's going to happen then is I'm going to create an electric field, which is going to point like this. It's going to be my electric field. But Brisson is also right, because what's happening is I'm pulling charges from here. So I have positive charges moving from this side to this side, which means I'm also creating a current. So I'm going to have a current running through. So my current is going to be pointing in this direction. This is going to be my current. Now, if I have a current, that also means that I have a magnetic field, which is what Brisson was saying. So in that case, I put my thumb in the direction then of the current. My fingers would curve around in the direction of the magnetic field, which means in this case, my magnetic field would be doing what? Curling around in this direction, which means that on this side, I'm going to have magnetic field lines pointing into the hole. That's my magnetic field. Now, eventually what's going to happen is what? The charges are going to eventually reach maximum flow, which means they're going to get maximum current, which is then going to give me a maximum amount of charge on this side and a maximum amount of charge on this side. But when that happens, then it's going to turn around and start doing the opposite thing. So eventually what's going to happen then is that the charges here are going to start to decrease. Charges here are going to start to decrease, while the current is also going to get smaller, until eventually the charges are going to move in the opposite direction since this is AC. So this thing is going to become positively charged on this side and then negatively charged on this side. So all of these things are going to switch opposite directions. Because now my current's going to be going downward, so my B field will be coming out. My electric field would then point in this direction. So eventually what would happen is my electric field is going to change directions and point in this direction, while my magnetic field is also going to change direction and then point in this direction. So let's think about what's happening. So let's draw the magnitude of both the electric field and the magnetic field. So this was my electric field as a function of time, and this is my magnetic field as a function of time. So again, initially I'm going to have zero magnitude of my electric field because that has zero charge. But then the charges are going to slowly increase, which means that my electric field then is going to start getting bigger over time. So I'm going to get something that starts looking like this. Until eventually I reach my maximum electric field, at which point in time it's then going to steadily decrease until again it goes back to zero, and then it's going to switch sides and then start doing the same thing on the opposite side. So overall, my electric field is going to do something like this. Magnetic field, again, it starts off with zero current. So my current in this case is going to be zero. But again, as the more charges build up, meaning I'm going to flow more and more charges, the current is also going to start to increase, which means I'm going to simultaneously get a magnetic field that's doing something like this. Until eventually, again, the current is going to switch directions, and then this is going to flop directions. So again, this is my magnetic field here as a function of time. So good. So what happens here? So what's happening here then is that what? We're getting a pattern. Right? So my electric field is going to end up doing something like this, and my magnetic field simultaneously is doing something like this. Right? So what kind of curves are these guys? They're sinusoidal curves, right? So what this basically tells me then is that, well, the magnitude of the electric field then is going to be equal to some amplitude. Let's call that E0. So that is the greatest amount of electric field here, times then sine of k times x minus omega t, because this is simply a wave. Simultaneously, my magnetic field strength is then going to be equal to what? B0 times then sine of also k times z. It's moving in the z direction, minus omega t. So basically what happens is what? I'm making two sinusoidal curves, but these two sinusoidal curves are exactly in phase with each other. So what I'm going to create from this is actually a wave where each one of these is creating its own wave. The two waves are in phase with each other, but they're actually going to be perpendicular to each other. So what this creates for me then is, again, light, which which as we showed before, it's going to look something like this. So what I'm creating in this case then are two waves simultaneously, where this is my electric field, this is my magnetic field. They're perpendicular to each other, but they're completely in phase with each other. So this is light. So light is, again, two waves superimposed on top of each other, perpendicular to each other, but they're exactly in phase with each other. Now, what that also does, in this case, is it creates radio waves. So if I match these guys on top of each other, I'll show this in just a second. So basically what happens is if I follow this pattern here, since the direction of the electric field and the direction of the magnetic field are constantly changing, what's eventually going to happen is that these electric field lines, which are moving in this direction, are going to superimpose on top of these electric field lines here, which means what happens is then as it moves outward, these are going to start to create closed loops that look something like this. And that's what this picture is showing. So for a radio wave, what ends up happening is, again, the electric field lines moving in one direction, and then as they move in the other direction, they'll superimpose on top of each other to create these kind of closed circles that are going to propagate away from the radio wave or from the antenna. So this is actually a radio wave. Now, eventually what's going to happen is as these waves move further and further and further and further away from the antenna, the size of these circles is going to become bigger and bigger and bigger. They're going to kind of stretch out. As they stretch out, what will eventually happen then is that the radius of the circle will effectively end up becoming infinite, which means that these circular waves here end up turning into what we call plane waves. Right? So eventually what's going to happen is the further and further I get away, this radius becomes so big that my waves are going to start to move in lines that look like they're parallel. So this is what we call plane waves. When this happens, this is what we call the radiation field or the far field limit. This is the radiation field or the far field limit. So any circular wave, like what's being created here, will eventually move out so far that it's going to become stretched so much that these things will effectively now becoming plane waves. So this is what we call plane waves. And this happens in what's known as the radiation field or the far field limit. Now, when we start looking at optics later, this is the region that we're going to start looking into. We're always going to be far enough away from a source so that the circular waves which are actually created are going to get extended so much that we can approximate them as simply plane waves. So we're always going to be working in this far field limit. What's up, Chris?
So after plane waves, do they just disappear over time?
Well, eventually they'll dissipate, yeah, depending on the absorption and other things in the medium. But yeah. Good. So let's also talk about some other things. So notice also the direction of the wave as it's propagating is actually moving in this direction. Now, if I use my right-hand rule, what I can see is what? If I put my fingers in the direction of the electric field at some point, let's say in this point, it's moving in this direction. So notice if I put my fingers in the direction of the electric field and curl towards the magnetic field, my thumb then points in the direction of the wave propagation. So what's happening here is my light is moving away in this direction, but the direction of propagation is given directly by this product of the electric field crossed then by the magnetic field. So the electric field crossed by the magnetic field tells me the direction of propagation, which means it tells me the direction of the velocity of the wave. And we're going to explain that later. Okay? So let's talk about some properties of light. So it turns out that light, the speed of light is then equal to the ratio of the amplitude of the electric field to the amplitude of the magnetic field, which turns out to be equal to 1 over the square root of epsilon naught times mu naught. So this is actually the definition of the speed of light in vacuum. And as we talked about yesterday, this is roughly about 3 times 10 to the 8th meters per second. Now, what happens though is when it moves inside of a medium, so when it moves in a medium, what happens in this case then is that the permittivity of free space then becomes the permittivity of the medium, which is then equal to the dielectric constant times then the permittivity of free space, and then the permeability of free space in a medium then becomes equal to the permeability of the medium, which is then basically this guy. I'm not going to say what it actually equals to. But basically what happens then is inside of a medium, the velocity then becomes equal to 1 over the square root of the permittivity times the permeability, which is then always going to be less than the speed of light. So we'll talk more about why this actually happens later, but just something similar to this. So what is light? So light technically is, so a lot of people when they think about light, what they think about is this type of light, which is the visible spectrum. So most people when they talk about light, what you really think about is the visible spectrum of light, which is about 400 nanometers up to about 750 nanometers. But that's not technically true. So light itself is actually the entire spectrum, which goes from technically 0 frequency all the way up to infinite frequency. So this is actually what we call light. So light is anywhere all the way from 0 frequency all the way up to infinite frequency. This is the entire spectrum of light. So again, most people when they talk about light, they really think about only this little tiny piece here, which is the visible spectrum. But that's not true. It's actually all frequencies of light are technically light. So this is the electromagnetic spectrum, going all the way from 0 frequency all the way up to infinite frequency. The difference is basically the size of the wavelength. So for this side, which is the radio side, you're talking about wavelengths which are anything from the size of the Earth to about the size of your hand. So this is all what constitutes then the radio wave. So again, remember that they're inversely proportional to each other when we talk about waves. Remember the speed is equal to the wavelength times the frequency. So as the wavelength goes up, the frequency goes down. So these are your very, very low energetic waves. In this case, then we have microwaves. Microwaves are from about the width of your hand to about the size of the pin head. So this is what you use microwaves to heat things up with. That one has a wavelength about the size of a grape, typically. So it's about that size. That's about the size of your wavelength. For submillimeter, that's going to be from about the pinhead size to about the width of your hair. For the infrared spectrum, that's going to be from the width of the hair down to about the size of a single-celled organism. Turns out that light, or visible light, is about the size of a single-celled organism. So again, that's about 400 nanometers up to about 750, about 800 nanometers. Ultraviolet is then anything smaller than that. So it's about a single-celled organism down to about a molecule size. So this is what's generating that light. X-rays are then from molecules down to about the atom size, and then gamma rays are anything from an atom size to smaller. So that's where gamma rays actually come from. Also remember when we talked about last semester, every different wavelength has a particular color associated with it. So if I was thinking about colors and temperatures, these size, the radio waves, these are basically black, which basically means that you're talking about a temperature of about 0.01 Kelvin-ish to all the way out here to gamma rays, which is at about, what's that, 300 million degrees Kelvin. So again, each one of these corresponds to a particular color. Us as humans, we are in this range, infrared. So we correspond to a temperature at about 97.6 or about 31 degrees Celsius. So this is our particular range that we would actually give off color. So anything that has a temperature, again, gives off a color. Us as humans, we give off infrared, which is why we can't see each other without actual physical lights, because we don't see an infrared spectrum. But if you're using infrared goggles, you actually can see something that way. You can see the heat temperature that's at there. But again, this is actually the electromagnetic spectrum. It does go all the way from 0 wavelength all the way up to infinite wavelength, or 0 frequency, actually, on this side, all the way up to infinite. So this is the entire electromagnetic spectrum. Now, again, each one of these is traveling at exactly the speed of light, so 3 times 10 to the 8th meters per second. The difference is how energetic that they are. So the smaller the frequency, the less energetic that they are. Okay with us? So good. So from here, let's introduce some new quantities and let's talk about that. So the first thing we're going to introduce is what's known as the Poynting vector. So what's the Poynting vector? So the Poynting vector we're going to call S vector. So S vector is then equal to 1 over mu naught times the electric field crossed then by the magnetic field. So it's what's called the Poynting vector. So the first piece of information we can get out of this real quick is, remember on the previous slide, we said that if we took the electric field crossed by the magnetic field, that then points in the direction of propagation, which means the Poynting vector then tells me the direction of propagation of the wave. So since this thing here is proportional to the direction of propagation, Poynting vector points in direction of propagation. In the direction in which the wave is traveling. Now, but it also tells me a lot more than that. So what it actually tells me is, let's take a magnitude of the Poynting vector. Let's look at that. So let's look at the magnitude of the Poynting vector. So the magnitude of the Poynting vector then is going to be equal to 1 over mu naught times the magnitude of the electric field crossed by the magnetic field, which is then going to be equal to the electric field magnitude times the magnetic field magnitude divided by mu naught times sine of the angle between the two. But as we said a little bit ago, what's the angle between the magnetic field and the electric field? How do they travel relative to each other? 90 degrees, which means in this case, theta is going to be 90 degrees. So it's going to be the same thing then as the electric field times the magnetic field divided by mu naught. Well, what is that? Well, let's look at our units of this. Let's kind of figure out what's going on here. So remember, our units of electric field are the original one we worked with, a Newton per Coulomb. We know a magnetic field has units of a Tesla. And then finally, we know that the units of mu naught is a Tesla meter per amp. So let's use these and let's think about what then is the units of this quantity called the Poynting vector. So this thing is going to have units of a Newton per Coulomb times a Tesla, all then divided by a Tesla meter per amp. So let's look at that guy. So in this case, the Teslas are going to cancel each other. So that's going to go away. Good. So this is then going to have units of what? The amps here is going to move to the top. So this is going to become a Newton times an amp per Coulomb meter. But what's an amp by definition? So amp is the unit of what? Current. And what's current? Change in charge over change in time, which means an amp is actually a Coulomb per second. So good. So this is going to be a Coulomb per second, which means the coulombs are going to cancel. So it's going to be a Newton per meter second. Okay. So let's look at that. So it's going to be a Newton per meter second. But now what I'm going to do is I'm going to take this thing and multiply top and bottom by a meter. So this is then going to be a Newton meter per meter squared times a second. Well, what's a Newton meter? It's a joule, good. So this thing then has, let's go to this page. So magnitude of S has units then of joules per meter squared second. But what's a joule per second? Power, that's a watt. So this is actually a watt per meter squared. Now, why this is important is because a long time ago, we talked about something which had units of watts per meter squared, which is what we call an intensity. So this is actually an intensity. So what the Poynting vector magnitude actually tells me is that it tells me the intensity of the light. Right? So this means then is that the magnitude of the Poynting vector tells me the intensity of the light. Well, what's intensity? So intensity is, if I was looking at a cross-sectional area, so if this was my cross-sectional area, and this is my wave, which is traveling. So what the intensity, remember, tells me is what? The amount of energy per unit second, which is deposited onto this area by the wave. This thing is telling me. So if this is my cross-sectional area of A, then the intensity is the energy per second carried by the wave. Per unit area. So what the intensity basically tells me is it tells me about the energy of the wave. It tells me how much energy the wave is actually carrying. So this is what the magnitude of the Poynting vector is actually telling me. So it tells me at least two pieces of information. Number one, it tells me the direction at which the wave is traveling, thanks to the cross products. And number two, it tells me how much energy the wave is actually traveling, because we know all waves actually carry energy. Now, in a realistic situation, we're going to be talking about light and frequency of light, especially if we're talking about something like visible light has around the frequency of about a nanometer, or sorry, nanoseconds. What that means then is we don't actually interpret the frequency. What we're going to actually see is the average frequency. Or in this case, we're going to look at the RMS value. So for something which has high oscillations, so a highly oscillatory what we're going to see then is not technically the magnitude of the Poynting vector, but we're going to see the average of the magnitude of the Poynting vector. In this case, what we're going to see then is what? This is going to become the amplitude of the electric field times the amplitude of the magnetic field, all divided by twice of mu naught. Because this is going to be the average of two sine curves squared. From this, we can then define what's known as the RMS values. So we have the RMS value of the electric field and the RMS value of the magnetic field. So this is the root mean squared average of the electric field and the root mean squared average of the magnetic field. Now, the reason we're doing that again is because since the electric field is oscillatory as a sine curve and the magnetic field is oscillatory as a sine curve, what then has to be the average value of the electric field and the average value of the magnetic field? It would be zero, right? Because you have half the time it's positive, half the time it's negative. So the average of that thing would be equal to zero. So the RMS value then is the average of the square. Basically, make sure that this thing is not zero. So this thing is going to be equal then to the magnitude of the electric field divided by the square root of 2. This is then going to be equal to the magnitude of the magnetic field divided by the square root of 2. So this is then going to be the RMS value of the electric field times the RMS value of the magnetic field, all divided by mu naught. So for highly oscillatory source, this then is going to be our average, which is also equal to our intensity. So the intensity of the wave in this case will be related to its RMS value, not to its amplitude. What's up?
What happened to the 2?
Oh, the 2, because this is a 1 over square root of 2 here, 1 over square root of 2 here. So I'm writing this as 1 E0 over 1 over square root of 2, B0 over 1 over square root of 2, to then rewrite these in terms of the RMS values. So it's absorbed into the definitions of the RMS. Okay? Now from this, we also know that again, the speed of light is then going to be equal to now the RMS value of the electric field divided by the RMS value of the magnetic field. Because all we're doing is multiplying top and bottom by square root of 2 over 2, or square root of 2, which means they're going to cancel so that ratio will stay the same. So this will still be true. It's okay? So again, the Poynting vector is telling me the direction of propagation as well as the intensity or the amount of energy carried by the wave itself. So okay, so let's use this and let's do an example. Oops, wrong check. There we go. So this says radiation from the sun reaches the earth above the atmosphere at a rate of about 1,350 watts per meter squared. So that's the intensity at the upper portion of the atmosphere. Then it says assume that a single EMF wave, this is what we call monochromatic, which basically means it only has one frequency. And then calculate the maximum values of the electric field and the magnetic field. So let's draw our picture. So let's say here's the Earth. Here's the atmosphere around the Earth. Here's the sun. And again, sun is then giving off light rays, and let's say our light ray is coming in like this. Okay, so we're pretending this is monochromatic, so there's only one frequency which is giving off, and that's going to reach the upper atmosphere of the Earth. And here we're told that the intensity at this stage is 1,350 watts per meter squared. So for this, what I want to know then is what is the amplitude of the electric field and what is the amplitude of the magnetic field? So for this, what do we know? Well, we now know that the magnitude of the average Poynting vector, because again, this is going to be highly oscillatory, is equal to the intensity, which is just equal to this number of 1,350, which is also then equal to the RMS value of the electric field times the RMS value of the magnetic field, all divided by mu naught. Now, in this case, what I want is the value of the electric field and I want the value of the magnetic field. What I have here is what? One equation with two unknowns. But I also know that the speed of light, again, is related to the RMS value of the electric field and the RMS value of the magnetic field this way. So what I actually have is what? Two equations with two unknowns. So in this case, what I can do is I can solve for, using this, I can rewrite the electric field then and solve this in terms of the magnetic field, and then solve for the electric field. Or I can solve this for the magnetic field, rewrite this in terms of the electric field, solve for the electric field, and then find the magnetic field. Whichever way that you want to do it, it's absolutely fine. Which one do you want to do first? Magnetic? Great. So in this case, we then get that the electric RMS is then equal to the speed of light times the magnetic RMS, which means I'm now going to put this in here for this guy. So this is then going to become equal to C times the RMS value of the magnetic field squared, all divided by mu naught. But again, what I actually want is the amplitude of the magnetic field, which means from there, I'm just going to rewrite this guy as the amplitude of the magnetic field divided by the square root of 2 quantity squared, which means I'm going to reintroduce that factor of 2 into the. So we get then that the intensity then is going to be equal to C times the amplitude of the magnetic field squared divided by twice of mu naught. From here, we can then solve for the amplitude of the magnetic field. So this is going to be equal to the square root of twice mu naught divided by C times the intensity. This is going to be my magnetic field amplitude. So it's going to be the same thing then as the square root of 2 times mu naught, which is 4 times pi times 10 to the minus 7, times the intensity, which is 1,350, divided by the speed of light, which is 3 times 10 to the 8th. Look at my numbers. When I find any stands, I do. Number. This works out to be about 3.37 times 10 to the minus 6 Teslas. Okay. From this, going back a slide, we now know that the magnitude of the electric field is simply equal to the speed of light times that magnitude of the magnetic field. So then from here, we can say, well, the magnitude of the electric field is speed of light times the magnitude of the magnetic field, which is then going to be 3 times 10 to the 8th meters per second, times 3.37 times 10 to the minus 6th Tesla, which then works out to be 1.01 times 10 to the 3rd volts per meter. Okay. What's up?
So the frequency of the magnetic field and electric field are going to be the same, but the amplitudes are not the same.
Correct.
How does that relate to the spectrum in which they are, or does it not?
It doesn't relate to the spectrum. So it all comes back to the fact that the ratio of the electric field to the magnetic field, again, going back to what we wrote down back here, is always related by the speed of light. So it's always going to be true is that the electric field amplitude will always be bigger than the magnetic field amplitude by the speed at which the wave is traveling. And as long as it's traveling in vacuum, then it's going to be greater by the speed of light. So that doesn't change anything about the spectrum or anything. The spectrum only depends on the frequency, but the frequency is usually determined by the energy of the source which is creating it. So the higher the frequency is, then the higher the energy of the source that created the wave, which then the higher the energy of the okay. What's up?
So according to the speed of light is the root mean value over the electric root mean value over the magnetic.
But that's also equal to, from here, the amplitude of the electric field divided by the amplitude of the magnetic field.
Okay.
So that's why in the last step I didn't use the RMS. I just used
That's wrong.
the other one. Because remember that the RMS is related by one of the curves too anyways. So we just cancel out the one of the curves. Okay. So Monday we'll talk about the fact that waves also carry momentum. So we'll see how the momentum is related to this quantity of the Poynting vector as well. So it turns out to actually be related to the momentum. We'll talk about that. And then since it has momentum, that means we can get force out of it. We'll start looking at forces due to light. So other than that, have a good weekend, everybody. And I'll see probably only like half of you on the next. I'm sure other people might disappear. So thanks. Okay.
Are you? You're
Sure.
I think I got it figured out. So when I went back, that's so. Well, it gets jumbled up in there sometimes. You gotta go back and go, okay, where are we at again?
Sometimes it's hidden in there.
Yeah, so I think I got it. My first experiment is still a little off, but I think it was just something there. And I didn't get it that one.
Okay. That's fine.
Thanks a lot.
No problem. Glad you figured it out. What's up, ladies?
You talked to your colleagues